Hi folks, welcome back. So we're just going to go for some optimization problems here. So we've got a cylinder and it's got a fixed volume of 500 milliliters and we are looking to calculate the minimum surface area. Whenever we've got these optimization problems, we speak about maximums and minimums, and that means differentiation. Before we can do that, we need to come up with some expressions for surface area and maybe volume. So here they're actually telling you that the volume V is equal to pi r squared h. R is the radius and h is the height of the cylinder. Also, they're telling you what the surface area is equivalent to. It's 2 pi r h, which is actually the kind of outer part. Think about a kitchen roll or a toilet roll inner, and you cut it with a pair of scissors. Then you fold it out, you'll get a rectangle. That's what 2 pi r h comes from. But if it was capped on top by a circle top, circle bottom, circles of area pi r squared, so there's two of them, that's why it's 2 pi r squared. Also notice they mentioned milliliters, so we need to be working in units that we're used to here. So like centimetres, that would be the base unit, the length unit. We're dealing in cubic centimetres for the volume. So that means that 500 milliliters is 500 cubic centimetres. We'll take that on board. So there's our expression for the area, 2 pi r h plus 2 pi r squared. That's dependent on the radius. The radius can vary. So can the height. Okay, so we've got a problem here. We can't have both the radius and the height in the one expression here. We can only cope with one of them. Right, and which one is that going to be? And why? Like it says here, we only deal with single variable calculus. R and H means we got two variables, but they're connected. That's a good thing. So we can get rid of one of them and exchange it by an expression that involves only the other one. That's what we're actually going to do here. So the thing is, what we know is, we know certain things about the volume, the expression for the volume there, but we've got a specific value for it. Okay? We know that. Pi r squared h and 500. Forget about the units just now. Why don't we make them equivalent to each other? Because they are equal. They're one and the same. So there you go. So we've got an expression there that involves both r and h. Okay? So let's take a wee bit further. There's the expression. Why don't we rearrange it to get either r on its own or h on its own? I think it would be easier to get h on its own. Get rid of that pi r squared. Take it over and divide 500 by pi r squared. There you go. That's how it's got h on its own. Okay, just shove h up to the side there and bring back the formula for area. 2 pi r h plus 2 pi r squared. We know what h is. Let's replace h in the formula by 500 pi r squared. That's exactly what we're going to do now. Keep an eye on this. H is going to disappear and 500 pi r squared is going to be inserted in its position. Okay, put it in. Right, let's change everything to black. Let's simplify the 2 pi r times 500 over pi r squared, and hopefully your algebra can cope to get that. That's us now. We've got an expression for A only in terms of R. And they like to say it's dependent only on R. So A is a function of R. So we're going to go and find this minimum value. Right. So that means that we need to go and differentiate A in terms of R to get this minimum area. There's a function, 2 pi r squared is fine. R is on the bottom of the first part of 1000 of R, so we need to bring R upstairs. It's got the power of 1 when it's downstairs. Bring it up and it'll change sign. There you go. Let's go and differentiate it. I don't need to go through the rules for differentiating. Again, you should know how to differentiate that. A takes the row of y, R takes the row of x. A dash is y dash. Okay, you've differentiated it. We have a derivative here. So whether we're looking for a minimum or a maximum, we have to take our derivative, A dash, and make it equal to 0. That's the condition. Let's now go and force the condition. We'll force the condition. We've got two terms that involve R. We're going to have to isolate R, get R on its own. So I took R to the minus 2 downstairs, made the power positive. Let's start isolating R. I don't like having 1000 over R squared being negative. Take it to the other side. Okay, and I shall make it positive. And sorry for that little slip of the finger there. So I've just took it over there, made it positive. Right, but we've got R on different sides now. But the good thing is R squared on the right hand side is downstairs in the fraction. Let's bring it up. R squared will come up to multiply the R term. R squared times R is R cubed, so I'll have 4 pi R cubed equals 1000. Let's isolate R cubed, get rid of 4 pi, or get rid of 4. Okay, so new page, get rid of 4, 1000 over 4, 250. Now I can get rid of pi, take it over and divide, set it under there. So let's uncube R cubed, so the cubed root, or the power of a third. And hopefully you're not asking, why is it a power of a third? Well, that's just because one of our laws of indices. Right, okay. We've got a value of R here, 250 over pi. Put it in your calculator, see what it gives you. Then cube root it or power of a third. It will give you a decimal answer here. Or it might just say 250 to pi to power of a third. Whatever. It'll give you a number between 4 and 5. And we're going for approximately that, because I think it comes out 4.30 something or other. Yeah, so I've rounded it. This is sufficient for our purposes. If you don't want to go for the approximation, go for the value at the top, go for the 250 pi. 250 over pi a third. And let the calculator do all the work. Okay. So what we're going to do is you've got a choice, use a nature table or a second derivative test for this radius that will eventually yield up a minimum surface area. I'm going to go for a nature table. So we're going to look left and right of 4.3 here. And we're going to pick numbers left and right, probably 4 and 5 I think here. Yep, and we're going to put 4 and 5 into the derivative that we found. And before we do that, we just want to note that automatically under 4.3 is 0 because we forced the derivative to be 0 that yielded 4.3. Okay, let's look at 4 in the derivative. I don't care about the answer here. All I care about is it positive or negative. Is that less than 0 or greater than 0? That's less than 0. Okay, that's negative. That's all I care about. Next one, 5. And the derivative, is it greater than 0, less than 0? It's greater than 0, it means it's positive. We're taking a negative and positive. The negative goes under 4, the positive goes under 5. That's what's happening there. That lets you know about the tangent lines at 4 and 5 and at 4.3. So under 4 it's negative, that's the slope. 4.3 it's horizontal, under 5 it's rising. So that looks as if it's tracing out a curve which throws up a minimum turning point at 4.3, and that's what we were looking for here. So we do have a minimum area at r equals 4.3. Let's take 4.3 and so we're going to put it into the area formula, not the one that involves h, but the one we come up with when we replace the h, so it only depends on r. Let's put in 4.3 in here. We'll probably come up with an approximation, a decimal. So go for however many decimal places you need or you think the question requires. So I'm going for that, 348.73. Because it's an area, the base unit is centimetres, so it's centimetres squared. That's us finished. Next. Just so you have a little read of the question there. Talking about fuel consumption, it's modeled by a certain function, y equals. You can read that. Where x is a steady speed measured in miles per hour, and they want you to determine the maximum and minimum fuel consumption, which is y. So let's go for it. So we've got the function, but there is a restriction on x here. They're saying it must lie strictly between 5 and 25, inclusive of 5 and 25. If you get less than 25 or more than 25 for any of the values of x, you have to discount them because they're not allowed in this problem. Right, okay, let's go and get the max and min values. Take the function and differentiate it. By now, you should be able to produce that. There's our derivative. I'll not read it out. These values, these minimum and maximum values, they exist when the derivative is equal to 0. That's our condition. We've got a derivative, we've got a condition, let's force a condition. I.e. take the derivative and make it equal to 0. Done. Right, that's a quadratic equation because we've got x squared there. You can solve that by taking out the ABC values, put it in a quadratic formula, solve it. You could do that. I'm going to just do it another way. I'm going to get rid of here. Why can I multiply by 1,000? I can do anything by multiplying and dividing both sides because on the right hand side I've got 0. I'm multiplying it up to get rid of the decimals. Okay, now I'm looking at the numbers here and saying, well, can I actually do, maybe they're too big, so can I reduce them? Does a number divide into them? I'm thinking about 4. Let's divide it. I get that there. I'm re-examining the numbers. Can I shrink them down? I'm looking at the 6 in front of x squared. I think they're all divisible by 6. That's what I'm going to do there. Divided by 6. Right, okay, so we've got that there. That's fine. I'm thinking about factorising that, but you don't like having negative x squared. So what I'm going to do is just change the signs throughout, and that's the same as multiplying by negative 1. Change the signs, so, and just reorder things. So negative 250 will go to positive 250, 35x will go to negative 35x, negative x squared go to positive x squared, and rearrange. That's a quadratic, nice one, equal to 0. So give me two numbers that multiply to give you 250 and add up to give you 35. Forget about the negative. Two numbers that multiply to give you 250 and add up to give you 35. Are you thinking 25 and 10? 25 add 10 is 35. 25 times 10 is 250. Yep, factorised. Let's separate and solve. One bracket is equal to 0. The contents of other bracket are equal to 0. So for x on the left, x is 10, x on the right, x is 25. So we'll get two x values here. So that's looking good. If you use the quadratic formula, you should have come up with the same answers. But I didn't like to use those values of A, B, and C because they might have given me problems. They might have given you problems. But and this is a good little exercise for your algebraic skills. Okay? This is not about an assessment. This is about you. This is about your knowledge. Okay. I'm going to use a nature table here with 10 and 25. Top row is x, second row is derivative, third row is the nature. What way is the lines going, the tangent lines going? So I've got 25, so I'm going to look at a number between 10 and 25, a number to the left of 10, and a number to the right of 25. Let's pick the numbers, whatever numbers. Between 10 and 25, or sorry, the left of 10, 5, that's fine. 20 lies between 10 and 25, that's crucial. And 30, it's above 25. Okay. Below 10 and 25, you know the derivative is 0 because you forced that condition upon it. That's how you come up with 10 and 25. Right, let's take 5, 20 and 30 and put them into word derivatives. We only care about the sign of the answer. With 5, it was less than 0 means it's negative. Next one. With 20, the answer was greater than 0 means it's positive. Next one, 30. Pop in 30, it was less than 0 means it's negative. So negative, positive, negative goes into the second row next to the zeros. Okay, negative, positive, negative. There you go. It lets you know then the third row about the nature of the slope of the tangent lines at exactly 5, 10, 20, 25 and 30. Going down, going across, going up, going across, going down. That's kind of tracing out the curve around about the critical values of 10 and 25. That means there's a maximum, a minimum x equals 10. You're only looking either side of 10 here, either side of 10, and a maximum at 25, either side of 25. The slopes at the bottom. That's what we're looking at here. So that looks like we've done there. Apart from, we actually need to go and use the values of 10 and 25. So there's the original function y. Let's take the two values of x, 10, 25. I'm calling them x1 and x2 here, because I'm going to have two different values for y. So I'll put in 10 there, and I need to come up with a definite value here. So pop that in your calculator. And hopefully you get that there. And it's 4, put in the units, 4 gallons per hour, but I'm just going to specify that was at 10 miles an hour because that was at X value of 10. Next, put in 25 in the original function, and that will give us a value of y2, the second value of y. So that gives you exactly 17.5, and we need to specify here at 25 miles an hour. And that's us all done. Right, let's go for a third and last problem. Let's go for a little nice wee easy number here. There you go, oil drum. It's given by V equals 9/2r with pi r cubed. So again, you know by now the script. But the thing is, here's the question. What are the instructions? Go and get the exact value of r for a maximum volume. Ensure that it's actually equal to the square root of 3/2 pi. Right, let's go. There's our formula there. Differentiate it. You know by now how to differentiate things. Again, condition. For maximum or minimums, the derivative must be equal 0. We have a derivative, we have a condition, force it upon it. I can only see one occurrence of r, which is actually r squared. So we're just going to try and isolate it. I took the 3 pi r squared over there because it was negative. Let's switch it about. Let's get rid of the 3 and divide both sides by 3 to leave us pi r squared. Okay, gives you that. Right, and let's get rid of pi and get r squared its own. Let's divide by pi. So pi will go downstairs and sit next to the 2. Okay, we'll get r squared, let's square root it. And that's us all done. We have shown that r equals the square root of 3/2 pi. That's all they were looking for. So, with quite an involved question at the start, and maybe a shortened one secondly, I don't know. And then this final one here. The final one was good because they just gave you a function and says, go and find a maximum or a minimum, whatever it is, and go and hit a value. It's good if you get questions like that. So what I'm going to do here is I'm going to let you go. Okay, right. Bye for now, folks. Good night.